this case, the grayscale images, that is the cv2.cvt colored, then image1.cvt.color bg2 gray. It's basically used to basically read the files, to take basically showing the files in this format. Then we resize the images, that is the resized is equal to cv2.resize. Then resize function is used the original image to the our new width and the height. Then the image is the gray, comma, new width, that is the 250, and new height, that is the 250. So that is used for resizing the images. After that, we write this into the f1 image, that comma resize. We write in this folder. The resized image is basically saved again in this folder with the same name. If we have the 1.jpg, then after applying this step, the 1.jpg is saved as the 250 by 250 pixels in the same folder, and the original image is replaced by this resized image. And the exception as e is basically print. If any exception occurs, then it give you the exception ki it is not properly working. So plt.im show is used for showing the image. Im read, that is reading the image, and we have the new image is which have the 250 and 250 as a height and width of the images, which after the resizing. Again we have showing the another image which showing the 250 into 250. That means ki all images of the GBM are resized into the 250 by 250, which is defined by us. Now again same thing is applied on the LGG dataset. Again we can resize the images, we read the images and return into the folder for the LGG images. So we read this image, and showing the image shows that the image is into the 250 into 250. Okay, after applying the split resizing, we split the data set in the train, test and validation. For this, we have the input folder, the subset dataset JPG. This is the folder name, in which we have two subfolders, which is GBM and the LGG. So basically, we want to divide this dataset into train. In the training, we have subfolder, that is GBM and LGG. In the validation, we have the training and validation, and the testing, again we have the GBM and the LGG as the subfolders. For this, we have also defined the output folder, key in which folder we want to save after dividing the data set. For this, we use the split.folder library .ratio. In the ratio, we put the argument as the input folder. Then we also pass the output folder path, and seed is equal to 42. We define the 42 seed for node randomization. Again, if some cases, if I am running this code after 1 month, so basically same pattern, same images are going to the same folder. So it basically divide for seed. We define seed to fix the shuffling. And the ratio 0.7, 0.1, 0.1, that basically gives us the ratio is between training validation ratio is 70%, 20% and the 10. 74 training, 24 validation, and 10 for the testing, which is already discussed in the PPT. So this basically from this code we resizes the images and split the data set into the training and the validation. Now after dividing the data set, we have applied the CNN models. Now I am discussing here only one model, that is the VGG16 with CBM, that is the VGG16 with the convolutional block attention mechanism. For this, We have used the NumPy array for the numerical work, and CV2 to work with the images, and the TensorFlow. TensorFlow is the most important deep learning framework which is used to basically create the models, to train the models, and the keras, and these are two important framework for the deep learning models. You can also use PyTorch. PyTorch is also used for the deep learning work, for working with the deep learning models. If you want to work with the machine learning, then you can use the scikit-learn for working with the machine learning models. So TensorFlow, in the TensorFlow, we import layers because we want to add the layers in the model, and the model for the creating the model, and optimizers to here I am using the Adam, so I am using the Adam optimizer. If you want to work with the other optimizers, then you can also import the other optimizers, that is the RMSC or the other things. For the losses, we import categorical focal cross entropy or the categorical cross entropy. Okay, matplotlib is used to plot or visualization the data or the images, and Seaborn is also the visualization library. From the sklearn, we import the classification report, confusion matrix, F1 score or ROC AUC score. For this, this is the important library before working with the deep learning, this library. Okay, now we have applied the normalization, that is the 1 dot divided by 255, that is used to normalize the images which are basically taken into the range of 0 to 255. 0 denote to as the black, and 25 is basically 0 to 1, that basically 0 denote as a grayscale image, 0 black, and 1 for the white images. For this, after applying this, we have applied on the training validation dataset or the validation dataset. In the training validation, we have defined the input for the models. Input for the models, the target of the model is 250, 250, and the color mode is equal to grayscale because our MRI and CT scan are in the grayscale images, and the class mode is equal to categorical because we want to differentiate between the GBM and the LGG, and we also take as the binary classification that give you the for the categorical we have to use the sigmoid. For the categorical, GBM and the classes classification prediction, it basically give the probability that between the range. If the the probability is high, that means it belongs to the that specific class. And the batch size is 32, and the seed is the 42 for the not the random shuffling. Again, the same thing is applied to the validation data. So after the normalization and the take and creating the input for the model, we have defined the input as the 250 image size 250, batch size is equal to 32, and the number of classes 2, epochs is equal to 30. We have defined three things for the CBM model. First thing, we have defined the block of the attention block, and second is the spatial attention, because CBM has two blocks. One is the channel, that is, and the second one is the spatial. For the channel, we use layers dot global average pooling. That basically define as we taking the global average pooling layer, the dense layer with the activation function is ReLU, and the again dense layer, and the activation function is the sigmoid, and reshape the images, that is the 1, 1C and the S, and return the layers dot multiply the X, that is the input feature, or the S, that is the reshape chart of the VGG16 with CBM, and that basically element wise multiply the input feature reset feature, and this input now pass to the spatial block, that is in which we have the average, that is we take the reduce mean and the reduce max and concatenate these two results into one, and then we have used the convolutional layer, that is the 7 filters padding same means ki we apply the 0 0 0 on the all the things, and the activation is the sigmoid and return as the multiply of the x, the input feature, comma the this featured map. And in the last one, we have called the CBM function. We define the CBM model in which we call the spatial attention block. And we already discussed that in the presentation, we have main 3 blocks. This is only for one CBM block, but basically VG16 with the CBM have main 3 components. First one for the feature extraction, that is we use the VGG16 and the CBM block and the classification head. So for this, we use VGG16 model for feature extraction. Here I am including top is equal to false, means ki we want to basically freeze some layers of the VGG16 to fine tune the model for our specific problem. And weight is equal to none. Weight is equal to none means ki if we use the weight is equal to image net, that means the ImageNet has the weight for the RGB images. And okay, now weights is equal to none means ki we want to take the weights of the ImageNet. That means ki if we take the image of weight of the ImageNet, so actually originally the VGG16 trained on the ImageNet and the weights of the RGB, but we have the grayscale images. For that purpose, we are not taking weights is equal to ImageNet because ki RGB weights are not useful for our grayscale images. That's why we are not taking the ImageNet weights. So that's why we're taking as the none. Now the input save, we define the over input size, that is the 250, 250 and 1 for the grayscale channel. Now the CBM, the main block in which we have built the backbone, that is the VGG16 model, which basically extract the features from the input image. Then we take the input as the CBM X, this block, that is the CBM block, which has the 2 main components, that is the channel wise or the spatial attentions. And then we have basically used the global average pooling, that is the classification head block, in which we have the global, we have the dropout, and we have the dense layer. So that's in this way we define the our VGG16 with the CBM model. Okay, after creating the CBM model VGG16 with CBM, we have trained the models on the basis of input. So we basically start with the callbacks dot model checks. Callbacks model dot model checks. We are taking the save best weights, monitor for the validation accuracy, mode is equal to max, or verbose is equal to 1. That model checkpoint means ki we apply for the early stopping. For early stopping means ki we want to train the models, but in some steps, if we get the accurate accuracy and the validation accuracy is not basically not implicitly taking as the max validation accuracy from that. And early stopping, we take again patience 7. Patience 7 means ki we want to basically train the models like we have first epoch, second epoch, third epoch, fourth epoch, and continuously at the seventh epoch, the validation accuracy is not improved. So in this case, we have basically we take the patience is equal to 7. If the validation accuracy is not improved, then the training is stopped, and the restore the weights that are the best. We also use the reduced learning rate plateau. For this, we also factor is equal to 0.5, monitor is equal to validation accuracy. So we have tuning the models. We have applied the hyperparameter, how we train the models. If the model not improving, then why we waste our time? We can stop the training and we can apply some hyperparameter tuning or some other optimization technique for improving the accuracy. So that's why we apply the early stop or the model checkpoints. Now we train the models, that is the history is equal to model dot fit. The model dot fit is basically used to train the models. Okay, so in this case we have passed two things. First one is the training data, validation data, and the epochs is equal to, we are taking epochs is equal to 30, which is defined above, and the callbacks is equal to CB, that we have defined the CB list, that is the model checkpoint early. Yes, Bhargavi. What background tools, software in the programming, mathematics, and medical images is necessary to conduct an AI-driven imaging study or performing? Okay, for working with the image analysis, you have to learn about the OpenCV library or the Pillow library. These two libraries are the more popular libraries to working with the images data set. Like you want to apply the resizing, you want to apply the filtration, you want to apply the other image processing task. So you can use the OpenCV and the Pillow library. If you want to work with the models, so you have to learn about the TensorFlow or the Keras. And another library is PyTorch. So from the TensorFlow and the PyTorch, you can select one which is more easier. I am using the TensorFlow for the deep learning work. And another work for the another analysis, you can have to some knowledge of pandas, you have to some knowledge of numpy. Numpy is basically used if you want to work with the pixel of the array of the images, you have to know about the numpy to work with the image pixels to find the means or the other things.
Sapna, actually, your cursor is blocking some of the code. So I just want you to use some other highlighter instead of that cursor you are placing on the code itself.
uh, from which point, from where, ma'am? I am now at the training part.
Like the pointer or the cursor which you are placing on the code,
Yeah.
sometimes it is blocking for me to understand some of the words.
Okay, ma'am. Okay,
Yeah,
okay.
can you please keep that cursor outside the words or you can use some other space.
Okay, ma'am. Okay, okay.
Thank you so much.
Okay, ma'am. Okay. After applying the define the callbacks or the training model things, verbose is equal to 2. We have save the weights. We have saved the model dot save. That means ki we want to save the model trained model. After working with training, we want to evaluate the model, we want to test the model after some time. So we have saved the models, we have saved the weights of the model. So for this, if I am training the model at this time, so then I want to work with the models after 1 month. Okay, now I have data set, the test data set like TCIA, TCGA, GBM, and the LGG. But uh, if in case I want to test the data set on the external data set, so I basically to fetch the external data set, it takes time. So how gaining train the models, everything is taking too much time. So we can save the models, we can save the weights of the model, and if we collect the external data set, then again we just load the model and test on the external data set. So that's why for the further purpose we save the model on the .h5 file, and the save the weights at the name as the file name .weights the h5. Okay, after training the model is trained. We call the train function the CBM model, and we save as the saving model is VGG60 CBM. Now the model is trained at the epoch 1, the validation accuracy is 0.95, saving the model to the checkpoint. Now again, the step 2, the improved validation accuracy is 0.95634 to 0.892215. So that means the validation accuracy is increased at this step, then this save to the model checkpoint. So this basically we define the 30 epochs. So that means ki 30 epochs the model is trained on the steps of 30. So steps of 30 we run the models, train the models, and after training, at the 18th epoch, the model is early stopping. The reason for that is the model is trained sufficient. So at the model is not improved. That means at the 11th epoch, the validation accuracy is improved from 0.996092 to 0.99657. After the 11th epoch, the 12, 13, 14, 15, 16, and 17 and the 18, the validation accuracy is not improved. So we define the early stopping, the patience is equal to 7. So that means it checked for the 7 steps. If the validation accuracy is not improved, that means we can stop the training. So it means the model is trained efficient, and now the validation accuracy is not improved on the unseen data, then we can stop the training. So now the training is stopped. Or for this training purpose, it takes 8 point, almost 893.37 minutes for training the model. Okay, now after they train the models, we want to visualize the results. We want the validation accuracy. We want the validation accuracy. And for this point, we call the CADD, that we have defined in training, that is the CBN net variable, in which we have model and the validation accuracy. For this purpose, we want to show this. We use the plt dot matplotlib for the visualization. So matplotlib is basically used for the visualization. We have the epochs, and we have the loss curve, and line width is basically that defines the width of the line in our graph. So that's why basically it define this line, that is 3.0. If you want the more thicker line, you can increase the size of the line width, that is 4.0, 5.0. If you want to thin line, so you can minimize the line width, that is 1.0, 2.0. So according to your purpose, you can define the line width. And font size is basically the 18, we are choosing 18 for the whole, the title, the ligand, training loss, and the validation. So we define the font size is the 18. You can increase or decrease the font size. And the plt.figure fig size is used to define the size of the visualization of the plot, 8,6. That means ki height is 8 and width is 6. If you want to bigger plot, then you can change to 10 to 20 according to your point. If you want broader plot, so you can change the size of the plot. That is the plt dot figure the fig size. This is I am using 8,6. So you can also change it. So this basically give you the loss curve and the accuracy curve, which are basically defined from the individual's epochs. So suppose at the training accuracy at 0th epoch, that is the increase from 0.802 and it is significantly increased, which is approximately 99 point something. And the same way, the blue line validation accuracy is starting from the 87 something, and then have the approximately 98 point something validation accuracy. So this is the plot for the validation loss curve and the accuracy. Now if you want to check the area under the curve AUC, you can also plot the same thing. You can call the history of AUC and the validation AUC. So it give you the area under the curve plot, and all things are the same. The line width, line font size, fig size, and all things are the same as the accuracy plot. Now the data model is trained. Now I want to testing the models on the unseen data, that is not basically give at the training time. That means we want to give the unseen data to evaluate the model on basis model is perfectly or effectively test or basically classify the images into GBM and the LGG when we give the unseen data, which is not provided at the time of the training. So we use the over 10% images which are divided into the testing set. So we take that 10% for the testing purpose. So here same we have applied the same normalization things, pre-process thing, input stream for the testing, which is applied for the training and the validation data set. Now after after creating the input stream, we have evaluate the model. The CBAM net, which is the variable in which we assign the training, we take the CBAM net dot evaluate. Dot evaluate is used to evaluate the data which we want to pass. So evaluate word is basically used for the evaluations purpose, that give you the accuracy of the testing data set in which we pass the test data set. So in this case we have the testing accuracy, it give you the 0.97 and the AUC area under curve is 0.9964. For this purpose I am okay. This one is for the CBA M net is dot evaluate is used when we are working in the Jupyter notebook and the session is not expired. So then we can use the variables of the training in which we have passed the training, we can use the CBA net. But in case we want to test the data on the after 1 month, that in this case the Jupyter notebook is not activated, right? So we basically again we use the Jupyter notebook after 1 month on the external data set. So you have to load the data set. The CBAM net dot evaluate is not working here. It give you the syntax error because CBAM net is not defined. For this purpose we used the saved model. After training the model, we save the model into .h file, h5 file. So basically we load the model. So for this we use tf.keras.models.load model and name of the model, which is saved into the .h5 format. Okay, after loading the model, we can use the we have to use the word predict to predict the data set. So predictions, for the prediction we use the test data set. It give you the list of the predictions in which it give you the probability for the each class. The probability is high for one class, that means it belongs to the that specific class. So in this showing only few numbers, that give you 1.000 plus 0. Second one is 3.750 and e raised to power minus 40. In this case, the probability of GBM 0 has the higher probability. That means it give you the this is belongs to the GBM. If it so that basically give you the probability for the GBM and the LGG class. Now I want to share this predict results. So we use the CSV for saving the prediction result for the further analysis. So VGG16 CBM underscore prediction. This is the name of file. You can change the name of the file as per your choice. I'm using only for the recognize well. This is the prediction accuracy of VGG16, or if I'm using the transformer, so I'm using the VGG16 underscore transformer underscore prediction. So this is just a name of the file. You can choose write your file name as per your choice. So I am using VGG16 CBM prediction.csv to save the prediction result. So I want to share this prediction result into the prediction VGG16 underscore CBM, and delimiter is comma because CSV is a comma delimiter. So I am using delimiter is equal to comma. If you want to save into the text file, so you have to use delimiter as a tab, that is a forward slash, because text has a delimiter as a tab delimiter. So you want to save the results, then you can use this. Okay, after this, I am finding the testing AUC, ACC, or the F1 score. So I am using the predict Y probe, all the that have the index 1, that I want to find out the probability of one thing, and then test the data set dot classes. Dot classes means you have two class. So it call you the automatically the classes GBM and the LGG in the testing data set. And if the probability greater than 0, type as the int, and test accuracy ROC and the accuracy score, that is the Y true. That is the Y true is the your actual label, and the Y probability is the your prediction label. That means if you provide two things, you have to want to predict the things, that is the predicted things is matched to the your true label, that means the Y true. And if prediction is not matched to the Y true labels, that means you have the misclassification. So you check for the this one ROC AUC curve F1 score, and for this it give you the AUC of 0.973, and accuracy testing accuracy is 0.9 and the F1 score is 0.9656. That basically give the F1 score is for the it is for this purpose, it is basically give you the harmonic mean of your precision and the recall. So when we check for the evaluation of the model, we check for precision, recall, and the F1 score. So F1 score is the harmonic mean of the precision and the recall, that is the 0.9656. Okay, if you want to check the all the classification report in which you have the precision, you have the recall, you have the F1 score, and for that you can use the classification report, in which you have the classification report function, in which you can pass test it. And this classification report is basically import from the sklearn library, which is imported in the starting of the code. So we call the classification report. In the classification report, we have test data, and we have the predicted class, and we have the target class. The target class are the actual target class are the GBM and the LGG. So in this case, it give you the precision, recall, F1 score of each class, which we are basically discussed in our PPT, the all the precision, recall, and F1 score of each class for all the models. So it give precision for the GBM, it is 0.98 by the VGG16 with CBM, and LGG is 0.97%. Okay, after that we have finding the confusion matrix. In the confusion matrix, it give you the course true label or the predicted label, true positive, false positive, or the true negative or the false negative in the term of this. So it is the 0 0, that is the true positive, that is the false positive, and this is the true negative, and this is the false negative. They basically give the TPFP or NP. This is all about the VGG16 with the CBM, how we define the layers for the CBM, and the how we train the models, how we visualize the results of the models, and how we evaluate on the testing data set, and how we find the classification report of the models. Okay, in the PPT we have already discussed कि we have ensemble the framework. That means कि we have used 4 models to ensemble. So basically AlexNet, VGG16, VGG16 with CBM, VGG16 with the transformer. For this purpose, I am showing here only one training model, but all the rest of 3 models are trained on the same experimental settings, like the number of epochs, number of the batch size, and the number of the hyperparameters, number of the things. So basically all the are trained on the same input data and same hyper settings. So for the ensemble, okay. Now, for the ensemble model, again, we are importing the important libraries which are useful for our work. That is the OpenCV library, NumPy, TensorFlow, Matplotlib, Seaborn, and the sklearn to work with the deep learning models. Okay, now to ensemble the framework, firstly, we have load over trained models. We have trained the model AlexNet, VGG16, VGG16 with CBM, VGG16 with the transformer. So we have load the model one by one. So firstly, we have load VGG16, AlexNet, then VGG16 with CBM, VGG16 with transformer. So each models are loaded. Now, after load the models, the ensemble model is basically work used for the testing data set, because the ensemble model use the logit of the prediction of each models to mitigate the biasness of each models. So we basically apply for the testing data set. So again we have used same input stream for the testing purpose. For the ensemble framework, same target size, color mode, class mode, batch size, and the SID. So in this case, we have y true, that is the 0 or 1. Now I am using the models to ensemble the models, in which we have the VGG16 baseline, AlexNet, VG16 transformer. That basically only give the type of the models. That is the, like VGG16 is a sequential model, and the AlexNet is a sequential model, and VGG16 and VGG16 with transformer and the CBM are the models. That means ki these are these have consist of 3 blocks. So that's are the not sequential models. So in which we have first thing is the VGG16 CBM block and the classification head. That's why it give you the model, not the sequential model. Now, applying the ensemble framework, we predict the models. We find out the predict the model, that is the M, and with DS, this verbose. DS is the basically defined as a one model, one by one. Then if p dot n dimension, that p dot n dimension greater than 1 and p dot shape 1 is equal to 2, it take class positive. Elsewise, p is equal to p dot revel. That means कि if you want to check for the GBM or the LGG class, so that predict the values, that p is equal to the predicted value. So that means कि if the dimension of the p is greater than 1, that means belongs to the positive class. If dimension of the shape of the 1 is equal to 2, that means it belongs to the positive class, that take as the positive class, that is the GBM. So we have defined the predicted logits or the ensemble probabilities. Ensemble probabilities, after finding the logit, we have applied for the transformation of probability. We apply the sum, that is the predict logit of the models divided by length of the models. So that is we apply for this, and find that's basically written as 1 upon 1 divided by 1 plus np dot exponential of log it. So that is basically give you the result for the ensemble probabilities. Now after these things, after applying the ensemble framework, we can check for the classification report or the accuracy report. For the classification report, again we call for the classification report, that is the y true, predicted class, and the target names, that is the GBM and the LGG, and the accuracy score, that is the y true and the predict classes. So it give you the classification report for the ensemble framework, in which GBM, the precision for the GBM is 0.99, LGG is 0.99. So in the same way, after train each models, AlexNet, VGG16, VGG16 with CBM, VGG16 with transformer, we have applied ensemble framework, which locate the prediction of each models and then transform it into the exponential of the log it. So basically the idea is that we want to mitigate the model biasness of each models to for the robustness of the models, to evaluate the models robustly. So we for this we apply the ensemble framework. So in the PPT we discussed that after ensembling we apply the grad camp. That means we apply the visualization to find that at the which location the model particularly focus to differentiate the GBM and the LGG. So before moving to the grad camp, we have the MCNMR test or the DeLong test. So after this, we have used, we apply the statistical significance test, that is the MCNMR or the DeLong. For the MCNMR, we installed the libraries, that is the stats model. In the stat models, we have inbuilt in the stat model we have inbuilt function, that is the MCNMR. So for this we use MCNMR test, we use stat models. So we basically installed this library for this purpose, because it is a external library, not is the inbuilt library. Okay, from this you import the combination, we import the MCNMR or the image data generator for the testing data set. For this purpose, we have the models VGG16, AlexNet, VGG16 with CPM, VGG16 with the transformer. So we apply all the things on the each models. So we apply the prediction on the each models. That means we apply, find out the prediction probability of each models for that purpose. After that, the ensemble prediction is applied. Now we can check for the MCNMR test. After applying this, the MCNMR test, we have Y true and we have Y prediction 1 and Y prediction 2. Y prediction 1 and Y, what is the Y prediction 1 and Y prediction 2? So we have the Y prediction 1 and Y prediction 2 means we have the prediction label for the one model and the another model. So we basically call the models for the check the probability of the pairwise model. So we have check for the Y prediction 1, and that means AlexNet, comma Y prediction prediction for the VGG16. We check for this and we apply the MC-NEMR test. So that means ki in this case, we have the probability prediction. This is the same thing which is applied in the previous slide in the ensemble. That is the MC-NEMR. In the MC-NEMR, Y true, Y prediction 1, Y prediction 2, that is the prediction. Y prediction 1 means you have to pass the prediction value of one model and the prediction of the second model. So if the Y prediction not equal to Y true and the Y prediction 2 is equal to Y true, that means ki model 1 is here wrong and model 2 is correct. So we check for the misclassification probability of pairwise of each model. If Y prediction 1 is equal to true and the Y prediction 2 not is equal to true, that give you the model 1 is correct in this case, but model 2 is the wrong. So this way we save this table, that is the B0, BC, 0. That means ki we save as a pairwise, that is the give you the result. And this MC-NEMR is basically create as a use this table, and exact is equal to true means ki you want this result as same this give you. Now the results dot p value comma b comma c. So this give you the p value of all the results. P value is basically defined from this one. We find the p of each one, that is the things. So basically the idea of is that we want to check that if we compare the two models, so on this basis, if the p value is less than for the comparison, that is 0.05, that means that model is significant or the not for this corresponding model 2. So we apply this MC-NEMR for the misclassification pairwise, check the misclassification pairwise of each model on the basis of probability. Now this give you this result which has already discussed in our PPT. Now we have applied the DeLong test. For the DeLong test, we have installed the library, that is the ML stat kit, that have the inbuilt DeLong test. So this give you the result for the DeLong test, in which we basically check for the Z and the P value. So in this way, we have applied the MC-NEMR and the DeLong test for the AUC difference of pairwise of each models. So it give you the, we find the model 1 M1 we append for. In this we check for the AUC1, AUC2, that is the model 1 and the model 2. So AUC we check for the ROC AUC curve for the first, second, and then Z is comma P value is equal to, that give you the call the DeLong test, which is taken from the ML stat library. Then it pass the value of Y true and the model probability of one and the model probability of second model, and return the confidence interval is equal to false, and return the AUC that is the false, and the verbose is equal to 0. These are the optional parameter. You can want to take, then you can use. So it basically give you the model 1, model 2, AUC of model 1, AUC of model 2, Z value, P value. If this significant, if P value is less than 0.05, it give you yes. If otherwise it give you no. So it check the pairwise AUC of each model. So DeLong test give you this result. Model 1, model 2, AUC of model 1, AUC of model 2, and the Z stat and the P value, and the check for the significance, that is the P value less than 0.05, it is significant, otherwise no. So we can save this result into the CSV file. Or after the MC-NEMR and the DeLong test, I think grad camp is maybe will not be completed in time. It almost have only 4 minutes. Then we can discuss in sometime in another session. Is it okay?
See if you can complete. Let's move fast so that.
Okay, sir. Okay, sir. I'll try. Okay. For applying the grad cam for each models, again we have importing in the important libraries for this task. So for this, the I already told you the NumPy is important library for work with the numerical task or the pixel array of the images. So NumPy is the important library. OpenCV is the also the important library to work with the imaging dataset, and the TensorFlow is the most important framework to work with the deep learning models. Okay. For the GradCam, okay, GradCam is what? GradCam, in the GradCam, we model GradCam basically generate the heat map of the models. So in the heat map, the model basically showing that on which area the model most importantly focus on the location to differentiate the GBM and the LGG. For this purpose, the for the GradCam things, we use the last convolutional layer of the models, because after the prediction, it is not necessary to apply the GradCam. The GradCam is used on the last convolutional layer, in which the features are extracted. The features are extracted means कि on the extracted features, the model identify that it is the GBM and it is the LGG. So GradCam is basically on the last convolutional layer of the model. For this purpose, again, we have load the all the models VGG16, AlexNet, VGG16 with CBM, VGG16 with transformer. So basically, we use all the models because we want to compare the models GradCam. So that's why we take all the models and we want to apply the GradCam. So first, okay. The first thing we do, that is the find the layers. Find the layers means कि the architecture of each model is different for classify for classifying the GBM and the LGG. So find the layers means if we want to find out at what stage or the sub layers which have the convolutional layer. So that means the define the function for finding the layers, pass the model layer name, sub model name is equal to none. So in this case we want to find in the main model. Main model means कि we want to find in the main last layer. Main last layer, if the layer dot name is equal to layer name, that is the convolutional, so check for L in the model layer, where the L check for the last layer for the model, that is the convolutional. If it is the convolutional layer, then it model give you the model dot get layer name and the model name. If the model in the model the last layer is not the convolutional layer, it check for the sub models. Sub model means in the case of VGG 16 with CBM, VGG 16 with transformer, or VGG 16s. In the VGG 16, the last layers are discarded for during the fine tuning. So in this case, the sub model check for the sub model the last convolutional layer. Again, if the not find in the main model, in the sub model is equal to model dot get layer. We find that, and this sub model pass the model. If the last layer is equal to layer name, so check for the sub model layer and return the sub model dot get layer. That means return the last convolutional layer for the sub model. Otherwise, it returns. If it is has some error,
और नहीं,
then
बस होने वाला था क्या?
yes sir.
अरे
Yes sir.
होने वाला था, उधर रुको ना, होने वाला है.
Okay sir. Sir, just give me 5 minutes only. So in the generated grade map, we check for the last layer. So then targeted layer is model, target layer, image tensor, target name or the submodel name, and the target layer and the layer parent name is equal to, we call the find layer model. In the model, the target layer and the submodel is equal to submodel name. And check for the gradcam model, we check for the tf.keras.models if the target layer dot output layer parent mode dot output. And now again, if we want to find out the gradcam heat map, we use the inbuilt gradient tape from the keras for predicting the heat map. So convolutional output comma prediction is equal to grad model image tensor. If the prediction dot shape greater than 2, then predict tf dot reduce mean, and the prediction that give you the prediction result. And again, this result save into the check for the tape dot gradient. And loss comma convolutional output, tf dot reduce mean, tf dot reduce cam for the grad cam, tf dot reduce sum. That these are the inbuilt function in the keras tensor flow for the grad cam. And the OpenCV dot resize for resizing the image. Then we pre-process the images, load the image into array, then ensure the channel for the models, image tensor and the model, and then define the function for gradcam for the ensemble model. Again, check for the last convolutional layer, and then create the overlay heat map on the images, the original image or cam map, and alpha is equal to 0, and it give you the heat map for the gradcam. Again, we use the save gradcam result. We want to save the result of the gradcam for the further analysis. Then the file is saved into the heatmap.png, and the confidence of the model .txt and gradcam.npy for the saving the gradcam numpy array. So these three things we want to save. In the main execution, the class label, we define the true label 0 if GPM or in image path else, or otherwise if 0 it is not 0, then it is the 1. We define the if condition. Then we have defined the gradcam for each model. We call the functions we had defined at earlier. After defining all the plotting model and all the things, we have call for the models. Then it gives the basically results that the 0.7311. So basically it give us the result for the confidence of the models and the gradcam heat map of the models. So in this case, the first model is the VGG16. So the original image is this. The predicted for this is 1. That means it is a GBM class, and gradcam also predicted as a GBM class, and it the overlay heat map focus that in this area the model focus for the visualization. That means the yellow or the red part shows that it is highly activated, and the blue color is basically shows that it is not participated in the prediction. So this is the gradcam analysis for the each model. So I hope time is over. So that's all for today. Thank you so much. If you have any
Okay.
question, then you can ask me.
Okay, so okay, so okay, let's see. Yes, participant, do you have any questions? Or yes, Sapna, can you save this, or can you share this with the participants so that they can perform on their own
Okay,
image?
okay, sir. I'll say. Uh, uh, so this work is under review. So
No
sir
problem.
told